We have one more law to add to our gas laws, and this is useful in a lot of ways. We'll just take a couple of quick glimpses at how we might use it. So I'm going to start over here with the triangle where we can see like what we see visually, what's going on with particles, and what's happening with symbols, and say that as you breathe in air, you're just thinking about breathing in air. And we are able to measure the pressure of that. So we could say that 1 atmosphere is the pressure of my air, but we don't know what's in it, right? We can't even see it really. So it's just a balloon of nothingness, but it's not really. So when we look at Dalton's law helps us start to understand that there's actually 2 major fractions to our air. So this pink I'm going to use to represent the oxygen molecules, and then in blue, most of what we're breathing in is actually nitrogen, N2. And then there's a 1% fraction of some of these other gases. But if we could look at the particles, we'd see tons of nitrogen molecules flying around, and we could see tons of oxygen molecules flying around in this proportion, 78% and 21%. That's going to be the same percentage at sea level here in Long Beach or up in the mountains. It's always the same percentage. Different pressures, but same percent. So that's the particle view of air. It's not just nothing. There's actually particles there. And Dalton's law takes this and puts it into symbols and would say that the pressure of nitrogen plus the pressure of oxygen, and we'll just ignore this 1% here, gives me the pressure of air. And so Dalton's law is that if I take the pressure of the fractions and add them together, I get the total pressure. And so this 1 atmosphere is what the pressure of all of those will add up to be. Here's another way of seeing that. So Dalton's law is saying that all the gases behave independently. So say I had a container of those oxygen molecules, they're going to have a certain pressure, maybe 1 atmosphere. And then if I have some nitrogen molecules, color those blue so we can see them, those maybe have a pressure of 2 atmospheres. So they behave independently, but then if I put them together, I can find out that the pressure would be exactly just simply adding them up. So if I have a bunch of nitrogen molecules, and then I have my 5 oxygen molecules, this pressure is going to be just the combination of the first 2. So that allows us to look at an individual gas or start to think about what a mixture of gases would look like. Conceptually, let's look at a problem that would relate to this. So this is a common chemistry setup where you heat something and then you bubble it into water and you capture it in a flask. Great setup, except you end up with a little bit of water vapor mixed in with your gas. So looking inside of this container here, I would have 2 things. I'd have some oxygen that I was collecting as one of my products, and then I would have this little oddball water molecule that was in there just because this gas was collected over some water in this bucket here. And so this says if the pressure inside of the flask is labeled 1 atmosphere, then that would be the total pressure of all of this together is 1 atmosphere. And I can say that that pressure is the combination of these 2, right? So 1 atmosphere is equal to PO2 plus PH2O. Just like over here, air is a combination of the pressure of the nitrogen plus the pressure of the oxygen. So the oxygen contributes and the water contributes, and together the total pressure is going to come from both of those. If we want to calculate something like this, when you add these up, you just have to make sure you're adding apples to apples, same units to same units. So in a dive tank, if there's 3 gases, nitrogen, oxygen, and helium, then that tank's pressure is going to be the pressure of nitrogen plus the pressure of oxygen plus the pressure of helium, and it asks for the total pressure. Now you have some flexibility since they didn't say what unit. As I look at these, you want to check your units: atmospheres, millimeters of mercury, and millimeters of mercury. So I'm going to stick with millimeters of mercury because that's what 2 of them are already in. So helium is 750 millimeters of mercury. Oxygen is 2440 millimeters of mercury. And then nitrogen is 3.75 atmospheres. So go look up your pressure conversions. 1 atmosphere is exactly 760 millimeters of mercury. And so when I work that out, I get 2850 millimeters of mercury. Now there's no decimal points with these numbers, so I'm just assuming that the zeros are all placeholders. And I'm going to take this 2850 up here now and add it to my little row of addition. So the units are the same all the way across, and that means I can add them up. And when I add them up, I get 6,040 millimeters of mercury. Or you could put that into scientific notation if you wanted to, right? Just practice that from the beginning of the semester. 6.04 times 10 to the third millimeters of mercury. That would be the same answer. And it would show the three significant figures very clearly. So that is Dalton's law. On the next slide, we will practice it in a larger problem.